Hi, back with me Gia Wulandari at Algorithm Strategy class. So in this video, we will continue our talk about branch and bound. And in the first part, we have discussed the general description of branch and bound and also an example about job assignment problem. And in the second video, we also talk about the use of branch and bound to solve a discrete knapsack problem. And in this video, we will see an example of solving traveling salesperson problem by using branch and bound. Let's get to the case study. So you should already familiar with traveling salesperson problem. So it is a problem where we have n cities or n nodes with their distances between each pair of nodes. And we need to determine the shortest path from one departure city such that all other cities are visited exactly once before returning to the departure city. So basically, we want to find a Hamiltonian cycle with minimum weight. In the previous topic, we have already discussed how we can construct a state space tree for Hamiltonian circuits. So basically for TSP, it is also similar. So if we have a graph with n nodes and we want to solve a TSP problem, we can write the solution as uh, V1 until Vn as V1, V2, V3, and so on until Vn and V1. So basically V1 is the departure city or departure or initial node, and V2 is the node that is visited directly from the first node. And then V3 is the node that is visited after we visit the node V2 and so on until we visit the last node. We go back to the initial node. So we can construct the partial solution like this. So we first, as initial step, we can determine which node is our initial node, and then step one, we can determine which node we visit the first time after from the initial node, and for the next step, we can determine which node we visit next, and so on, so that the level of the tree will represent the order of visit, while children represent the nodes we can visit. So, like the other case study, other than knowing how to construct a state space tree in branch and bound, we also need to know how to compute a bound for a partial solution. So let us uh, consider a TSP that already has a solution V1, V2, and so on until Vn and V1. Then, if Cij represent the weight of H from I to J, then the minimum total weight for the TSP problem is F, like this. So it is the weight from Vi to V2 plus the weight of H from V2 to V3 and so on until the weight of H from Vn to V1. So let's say we have something like this as the cycle. This is V1, V2, V3, V4, and V5. Okay, so let's say we have A, B, C, D, and E as the weight of them. So the total weight will be A plus B plus C plus D and E, right? That is the total weight, which is minimum if the cycle is the solution for the TSP problem. And this addition can also be written as two edges that is incident to V1, which are A plus E. And then we add edges that are incident to V2 in the cycle, which are A plus B. And then we add edges that are incident to V3, which are B plus C. Also edges that are incident to V4, which are C plus D, and edges that are incident to V5, which are D plus E. And because we add each uh, edges weight twice, so of course we need to divide them by 2. Okay, so what is the lower bound for this problem, for the minimum weight? We can see that here we add two edges that are incident to every node we have in the graph. You know, a Hamiltonian cycle is a cycle that contains all nodes of the graph. So here we add exactly two edges that incident to each node, which cannot be lower than the sum of two edges with minimum weight for each nodes, right? So the lower bound for the TSP can be written like this. So basically it is sum of weights of two edges that has the minimum weight for each node. If we have the partial solution, we just need to adjust the lower bound depends on the solution we have construct on that partial solution. Let's get to the example to have a clearer idea for this case study. So let us consider this graph for the TSP problem. So because this is undirected graph, then if we have, let's say, this Hamiltonian cycle, it will have this exactly same total weight as the mirror of the root, isn't it? So the weight of the first root will be the same as the total weight of the second root. So here, to have a simpler construction, then we can have a constraint or a rule. Let's say that C cannot be visited before we have visited B, so that we can have this as a solution. We immediately know that the second one is the solution as well. Okay, so we start with constructing the state space tree by having the initial node or the root node, which determines which node become an initial node. So here, let's say we have A as the initial node, and the lower bound will be the sum of two lowest weight for each node. So for A, the lowest weight is 1 and 3. So we have this. And for B, the lowest weight is 3 and 6. So we have this. And then for C, the lowest weight is 1 and 2. So we have this. And next for D, the lowest weight it's attached to is 3 and 4. So we have this. And finally, for E, the lowest weight we have is 2 and also 3. So we have this. And again, because we sum up the weight of two edges for each node, then we need to divide it by 2. And here we need to round it up to make sure that we will not miss the gap between this and the next integer. Okay, so again, like the other case study, here we choose an active leaf with the best lower bound, and because we only have one leaf, we don't have any other option. We check its children. For the next level, where we can go to and because from A we can go to B, C, D, or E, so we have these 4 children. So we need to compute the lower bound for each children. So a lower bound for AB. So for AB, it means that we have AB, the HAB, as the part of solution, which means the H that is considered attached to A must contain 3, and also another H must not lower than 1. So we have 1 here. Okay. And for B, again, we must consider 3 because it is a part of solution, and the other H that is attached to B in the solution must not be lower than 6 because we don't have any other H that is lower than 6. So we have this for B. Then for C, we don't have any solution yet that is attached to C, so we just need to find 2 minimum weight attached to it, which is 1, 2, and 2. And then for D, we do the same, we choose 4 and 3. And then for E, we have 2 and 3, like this. So we have the bound is 14. For AC, we do the for AC, we don't need to compute the lower bound because here it violates the constraint where C cannot be visited before B gets visited. But here we haven't visited B yet, but we visit C, so it violates the constraint. Next, for AD. For AD, we need to check the lower bound for that. So AD, it means that we have AD as the part of solution. So for A, 5 must be considered as the part of the solution, and the other H that attached to A in the solution cannot be lower than 1. So we have 1 plus 5 here. And for B, 2 H's that is attached to B in the solution cannot be lower than 3 and 6. So we have 3 plus 6 here. For C, again, we choose 1 and 2. For D, we choose 5 because it is part of solution, so it must be considered. And then we choose 3 because it is the lowest we have that is attached to D. So we have 3 plus 5 here. And E, here we can choose 2 and 3 because they are the lowest one that is attached to E. Okay, and AE, which means AE, this H is part of solution. So in the solution, A must be attached to 8 and also to an H that is not lower than 1. And for B, in the solution must be attached to 2 H's, and it cannot be lower than 3 and 6. And for C, the 2 H's that is attached to C in the solution cannot be lower than 1 plus 2. And for D, we can choose 3 and 4. And for E, because 8 is a part of solution, then 8 must be considered, and the other H must not be lower than 2. Okay, and here we have 3 leaves, And because this is a minimization problem, then we need to choose the lowest lower bound we have in this situation. And the lowest one is 14, so we check the children of it. So from B, we can go to C, D, or E. So for A, B, C, and because A, B, C is a part of solution, then A must be attached to 3, and the other edge that is attached to A in the solution cannot be lower than 1. So we have 1 plus 3. Then for B, it must be attached to 3 and also 6 based on the partial solution we have. So we have 3 plus 6 here. And for C, it must be attached to 6 and the other edge must be lower, cannot be lower than 1. So we have 1 here. Then for D, we don't have any partial solution that is attached to D yet, so we can choose 3 and 4 here. And for E, the same, we can also choose 2 and 3 here. Okay, next one, A, B, D, we do the same. So A, B, D is the part of the solution, so A in the solution must be attached to 3, and the other edge that is attached to A in the solution cannot be lower than 1. For B, it must be attached to 3 and 7 in the solution, and C has no edge attached yet in the partial solution, so we can choose 2 lowest edges that is attached to C, which are 1 and 2. And then for D, 7 must be attached to D in the solution, and the other one cannot be lower than 3. And for E, the 2 attached edges in the solution cannot be lower to 2 and 3 here. Okay, so we have 16 as the lower bound, and for the next option, A, B, E, we do the same. A, B, E means that for A, it must be attached to 3 and another edge that cannot be lower than 1. For B, it must be attached with 3 and 9. For C, it must be attached to 2 edges that cannot be lower than 1 and 2. And for D, it must be attached to 2 edges that cannot be lower than 3 and 4. And for E, it must be attached with 9 because of the partial solution, and the other edge that is attached to E in the solution cannot be lower than 2. Okay, so here we have 5 leaves, active leaves, and we want to know which one has the lowest lower bound. So we have 3 16ths here, but of course we will prefer to consider the lowest bound that is obtained after we have constructed more partial solution, because we have already checked more nodes other than what we have in the first level. Okay, so between the first one and the second one, we choose one of them. So let's say that we choose the first one, A, B, C, and we check the children of it. We can go to D or E from C, and it implicitly leads us to a final solution, because from D we don't have any other option other than go to E and then go to A. The same goes where we choose E, then we don't have any other option after that. We have to go to D and then back to the initial node. So because we already have the final solution, we just need to check the total weight we have for that final solution, which are 24 and 19. But it is still bigger than the lower bound we have here, which means if we continue this subtree, then we may have a lower final result than 24 or 19. So we continue with the A, B, D. We can go to C or E from D. And if we go to C, then we don't have any other option. Then we go to A, to E, and continue and back to the initial node. Or from E, we can only go to C before we go back to the initial node. And we can compute the total weight for both option, and we got 16 here. So we have 7 leaves where the lowest one is this one and this one. And again, because this has more nodes we have considered, so we choose this one. And because this is already the final solution, and for other final solution, they are not better than 16. And for the other leaves we have, if we continue the partial solution, it cannot be lower than 19, 16, or 19, which means 16 must be the lowest one we can have. So we already find the solution, which is the root A, B, D, E, C, A with total weight of 16. Okay, that's all for a traveling salesperson problem. You will need to, but to be noted, this is for undirected graph. For directed graph, you need to have some modification, but actually it is similar. So in undirected graph, you consider something like this, but in directed graph, it means that you need to consider something like this, which means for each node you can consider an outgoing edge, one outgoing edge, and one incoming edge for each node. Okay, that's all for traveling salesperson problem, and we reach our end for this topic. Thank you for watching, and goodbye.